AP Chemistry, this is the answers video for the Day 81 assignment that you were given on Wednesday, January the 12th. So this answers video, rather than me recording myself writing on the assignment, is going to be just up here on PowerPoint, and it's going to be every answer to every problem. I want you to resist just copying. I want you to try to understand the reasoning, listen to it carefully, study it, try to attempt the problem, at least get started on it first before you just watch the answer, and then understand how to do these problems. If you can master acid-base buffer problems, you're well on your way to passing the AP exam. So we'll go ahead and get started with this right now. Okay, so problem number one, this is the problem number one that's on your assignment. So what we're trying to do is up at the top. We're going to calculate the pH from the mass of an acid using the weak acid formula. So you should go back and review the last lesson and even just jot down the 5 formulas for strong acid, strong base, weak acid, weak base, and Henderson, Hasselbach. And you want to learn which one to use in which situation. So the question is, what is the pH of a solution by dissolving 15 grams of acetic acid into enough water to make a 1 liter solution? And you're given the Ka of acetic acid. So a couple of things about this. It only involves a weak acid, acetic acid. Therefore, you're going to use the weak acid equation on this. The second thing is, you'll notice you're given the measure in grams. And you need to ultimately convert that for the weak acid equation into some concentration of the weak acid, which is moles per liter. Now you're given the volume in 1 liter. So you need to have the number of moles of acetic acid. And you've been doing this since the beginning of class, is computing molar masses. So let's go ahead and get started. So first, compute the molar mass of acetic acid. Okay, and I didn't do that explicitly here, but you have 2 carbons, you have 4 hydrogens, and you have 2 oxygens. Go to your periodic table, get the molar masses of those, and you add those up. You get 60.06 grams per mole. So there it is right there for acetic acid. Now, you can convert that to an equivalency. 1 mole of acetic acid equals 60.06 grams of acetic acid. You can skip that step if you don't feel you need it. If you know how to get the conversion factor just from the expression over there, or the equation over there on the left, just do that. But if you want to write it as an equivalency, there it is right there. So now there's the molar mass conversion. You have 15 grams. The way you want to set up your ratio is 1 mole of acetic acid over 60.5 grams of acetic acid. The grams on top, grams on bottom are going to cancel, and you're going to end up with moles of acetic acid, and that number is 0.250 moles of acetic acid. So now you can use the weak acid equation. And now, since there's 1 liter of solution, 0.25 moles of acetic acid per 1 liter is going to be a molarity, a concentration of 0.25. So the number value doesn't change. So there we go down to the bottom and we plug it into the weak acid equation. We have the Ka value for acetic acid. In some of the problems in this problem set, I used 1.8 for acetic acid, some 1.75. It really doesn't matter. Times 10 to the negative fifth, and it's 0.25 molar because it's 0.25 moles per 1 liter of solution up there. And when you just do the math on that, you get the pH is 2.68. Okay, now you're going to do the same problem using a rice table. What do you need to know how to do it both ways? You should. You should know how to do it both ways. Normally, you just pick one way or the other, but we're going to do it this way. Okay, so there's your weak acid equation up there. You have a weak acid, HA. That's the generic abbreviated form of a weak acid. That H is going to break off the proton. So there it is over on the right, H+, that's the proton. And then whatever else is remaining from the acid, if it's acetic acid, it would just be CH3COO-. It would be the rest of the acetic acid molecule. So that we're going to call that A-. Okay. Now, if you know the formula for acetic acid, you could have written it, CH3COOH. But what if you didn't know it? Then you can always use, as long as you know it's an acid, you can always use this generic formula to do these problems. Okay, so we have a concentration of 0.25. We got that from the previous problem. We're going to start off with an initial hydronium ion concentration of 0 and an initial conjugate weak base concentration of A-. Now remember how the change line is done? It's minus because on the reactant side, the left, you're going to be decreasing the concentration, you're going to be using it up. And the coefficient is 1 because up above where the equation is, the reaction rather, HA, there's a 1 in front of the HA. So it's minus 1x. Over on the right side, it's going to be plus 1x because on the product side, you're increasing the concentration of the products. And the 1 comes from the reaction equation up above. And then the same thing for the A-. So now we subtract on the reactant side, so it's 0.25 minus x, and then 0 plus x, and 0 plus x. And there you have your equilibrium in algebraic form. Now we're going to go ahead and set up the law of mass action, and I'm kind of shortcutting everything here. I'm cutting out some steps. So over on the right side, it's x times x, which becomes x squared. On the left side, the reactant side, that goes in the denominator, it's 0.25 minus x, but I already eliminated the x because of the simplifying assumption. So I think you're hopefully all kind of comfortable with that right now. What that means that the x is so much smaller than 0.25, you can just pretend like it doesn't exist. So I did that right away. I didn't even put it in the law of mass action there. So now we're going to go ahead and just solve for x. So you multiply 0.25 times 1.75, and you get 0.438 times 10 to the 5th. Then you're going to take the square root of both sides to solve for x. And there you get x equals 0.00209 molar. So that's the concentration. If you look up on the Rice table, you'll see that the equilibrium concentration of hydronium is x. So now we can use that x equals the hydronium ion concentration at equilibrium to compute the concentration of pH. And so that's going to be pH equals the negative log of x, or the negative log of the hydronium concentration. And that gives you 2.68. Okay, so the same answer we came up with in the previous slide. All right, so just two different ways to do the same problem. It's just an exercise to practice. Be sure you're comfortable using both methods and that you see how both methods work. Okay, now up at the top it says calculate the pH of a common ion using a Rice table. So here we go. What is the pH of a solution containing 0.1 molar of hydrofluoric acid and 0.3 molar of sodium fluoride? So again, you're given a Ka value, that's the Ka for hydrofluoric acid, and you're going to use a Rice table. So first thing you got to ask, what happens to sodium fluoride when you put it in water? Again, you go to your solubility rules, and you're going to just kind of assume this is going to always happen when you see something like sodium fluoride, potassium fluoride, something, that it's going to break off. It's going to dissolve off. So that sodium is going to dissolve off, and it's just going to go off to the side. It's no longer a part of what we're doing here. So it's a spectator. So you are going to end up with a fluoride ion, an F-. So that's called the conjugate. It's called the common ion of hydrofluoric acid. Hydrofluoric acid produces a fluoride ion, and sodium fluoride produces a fluoride ion. Why did you put the sodium fluoride in? Let's repeat this. We've talked about this before. For a buffer, you want the same number of weak acid, in this case hydrofluoric acid molecules, as weak conjugate base, in this case fluoride ions, F- ions. But let's just say that for every 5 hydrofluoric acids you put in the water, only one of them turns into a fluoride ion. So you have 4 hydrofluoric acids, 1 fluoride ion. If you keep adding hydrofluoric acids, you're going to continue to get that same ratio, 4 to 1, 4 to 1, 4 to 1. So continuing to add hydrofluoric acid is not going to get you to your goal of having equal numbers of hydrofluoric acids and fluoride ions. You want to have the equal number. So how do you do it? So you find a compound that has 2 characteristics. One is that when it dissolves in water, it will produce the fluoride ion. That's what you want. So sodium fluoride meets that requirement. It has a common ion in water of fluoride ion. The second requirement is that sodium fluoride, every time you put one of those molecules in, sodium fluoride, it breaks off. The sodium breaks off and goes off to the side. So if you put 5 sodium fluorides in water, you're going to end up with 5 fluoride ions. That's what you want. You want to be able to add fluorides without adding hydrofluoric acid. And by doing that, by putting an equal molar of HF and NaF, you can end up with the same number of moles of hydrofluoric acid as fluoride ions, and that's what you want in a buffer. Now in this problem, you don't have equal molarity. You have 1.1 molar of hydrofluoric acid, and you have 0.3 molar of sodium fluoride. But every one of those sodium fluorides is going to break up and produce a fluoride ion, so you're going to end up with 0.3 molar of F- of the fluoride ion. So now we can go ahead and fill in our Rice table. So right there, hydrofluoric acid is 0.1. You don't do water. You don't include water. The fluoride ion, it says up there, is 0.3. The sodium fluoride was 0.3. That means the fluoride ion concentration is going to be 0.3. And the hydronium ion is going to be 0 at the beginning. Okay, so here we go. It's minus X on the reactant side. You're going to decrease that, and by some variable. Over on the right, on the product side, you're going to increase the fluoride ions by that same variable, because all the coefficients up there, I didn't write them in front this time, but it's 1HF, 1H2O, 1F-, 1H3O+. They all have coefficients of 1. That's the nice thing about acid-base equations. They always have coefficients of 1. Okay, and then the hydronium ion, H3O, is plus X as well. So now we go back to the reactant side, so it's 0.1 minus X on the equilibrium. On the product side, it's 0.3 plus X under the fluoride ion. And for the hydronium, it's just plus X. So now we're ready to write our law of mass action. We have our Ka value there, 3.5 times 10 to the negative fourth. So there's the general equation for it. On top is the products. That's the hydronium ion and the fluoride ion. And on the bottom, you exclude water, you have the concentration of the initial hydrofluoric acid. So now we're going to plug in the algebra expressions there. So you have on the top 0.3 plus X, and then times X. Coefficients are all 1, so you don't have to put any exponents down there in the law of mass action. And then over on the left side, that goes the hydrofluoric acid, that goes down in the denominator. It's 0.1 minus X. And as we can always do, those plus and minus X's we can eliminate using, that's the simplifying assumption. We assume they're much smaller than 0.1 or 0.3. So now what we'll have over here is the equilibrium, or the Ka equals 0.3x over 0.1. And now we're going to solve for X. So X equals the concentration of H3O plus. If you look up on the Rice table, X is in the equilibrium line below H3O plus, and that's what we want, is H3O plus to do our pH calculation. So there we're going to multiply the 3.5 times 10 to the minus 4 by 0.1 divided by 0.3. That solves for X, and that gives us 1.2 times 10 to the negative fourth. Since X equals H3O plus at equilibrium, then that means the H3O concentration equals 1.2 times 10 to the negative 4. So to get the pH, it's the negative log of 1.2 times 10 to the negative 4, and that equals 3.93. Okay, so that's the calculation of a weak acid and its conjugate weak base, not necessarily in equilibrium, just what you were given to work with there. Okay. Now we're going to do the same problem using Henderson Hasselbach. So what do we have here? What do you need for Henderson Hasselbach? So a common ion problem includes concentrations of both conjugate acid and base. This means that Henderson Hasselbach can be used because you have both. So if you look at the equation, you're going to need the pKa, the concentration of the weak base up on the top, inside the log, and then the concentration of the weak acid down on the bottom. Well, if you look at the problem, we already have two of those three. We have the concentration of the weak acid, that's the 0.1 molar HF, and we have the concentration of the conjugate weak base, that's the 0.3 of the fluoride ion. The only thing we need to do is take that Ka and compute the pKa. So the pKa is simply negative log of Ka. That's what P means, negative log of. So if we do that, the negative log of 3.5 times 10 to the minus fourth, I didn't show the calculation here, but do it on your calculator. Be sure you confirm this. Gives you 3.46. That's the pKa. And then you have the log of the base on top. Be sure you don't get it backwards. It's the conjugate base on top. That's the 0.3 of the fluoride ion. And the conjugate acid on the bottom. That's the 0.1 of the hydrofluoric acid. So now you just go ahead and solve for this, and you get 3.93, the same thing we got on the last problem. Again, it's just two different ways of doing the same thing. Henderson Hasselbach is much shorter and easier, but you do have to have some of both the weak acid and the conjugate weak base. If you don't have both, you can't use Henderson Hasselbach. You can, however, use the weak acid equation or the weak base equation, depending on which one you have. Okay, new problem. Calculate pH of a common ion using a rice table. Okay, so this is similar to the last one. So you have a solution containing 0.15 molar NH3, that's ammonia. Now you just kind of learn to recognize some of these common bases, ones that you see a lot. NH3, ammonia, is a base. So what is its conjugate acid? Well, since it's a base, it accepts a proton. That means the NH3 can take on a proton from, say, a water molecule or from a strong acid molecule. So that makes the NH3 NH4. And since it was simply a proton that it took, the positively charged proton, it becomes NH4 plus. That's an ammonium ion. Okay, so that's the conjugate acid of the base NH3. So now we look at what we have over there. We have NH4Cl. And we recognize that the NH4Cl is an acidic salt. It's a neutralized acid molecule. We just said that NH4 plus is an acid. It's a conjugate acid of ammonia. And if you neutralize that NH4 plus by taking a Cl minus and plus neutralize each other and stick it on there, now you have an acidic salt, a neutralized acid molecule. And you know also that NH4 from your solubility rules is always going to break apart from anything it's with, including that chloride. And so the chloride is just going to swim off to the side and be a spectator. So you will have your conjugate acid, conjugate weak acid, NH4 plus. So we can go ahead and write the equation down below. Now, since it's a Ka value we were given, we're going to write it as an acid reaction. Of the NH3 and the NH4 plus is the acid. So we're going to mix that with water. It's going to donate a proton to water, and then the NH4 plus becomes an NH3, an ammonia molecule, and the water becomes a hydronium ion. Now, we could have turned that reaction around and done it in the other direction, made it a base reaction. If we had done that, we would have to use the Kb rather than the Ka. You see, we were given the Ka. We would have had to use the Kb. We weren't given the Kb, but we can figure it out. Okay, we talked about how you do that. Kw divided by Ka will give you Kb. So I'm just saying you could have done this as either an acid or base reaction, but since we're given Ka, the acid dissociation constant, we're going to write it as an acid reaction. That means the acid is on the reactant side, NH4 plus, then the water, and then the conjugate base, NH3, after the proton was given away to the water molecule, and then the hydronium ion, which is the characteristic of any acid. It produces hydronium ions. Okay, let's go ahead and plug in the numbers. So the NH4 is, and so NH4Cl, what we just said, will immediately break apart in water to form a weak acid, NH4 plus. So that's the ammonium ion. Okay, so let's plug in the numbers. So 0.1 for NH4 plus. We don't count water. NH3, we're given a concentration of 0.15, and we assume no hydronium ions at the beginning. Now it's going to be minus X on the left, plus X and plus X on the right. So on the left, on the reactant side, we have 0.1 minus X. On the right, on the product side, we have 0.15 plus X and 0 plus X. Okay, so we're going to go ahead and write our law of mass action. There it is, and we're going to plug in the algebraic expressions. So convince yourself that those are correct. Products on the top, right side on the top, reactants left side on the bottom. Okay, of course, we can use the simplifying assumption now, and that gives us the actual Ka that we have up above in the question, 5.56 times 10 to the negative 10th equals 0.15x over 0.1. Now we solve for X. Okay, so X equals the hydronium ion concentration. That's what we're interested in if we're trying to get to pH. We want to know the hydronium ion, so it's the value of X. So that's simply going to be 0.1 over 0.5. I just multiplied both sides by 0.1 divided by 0.5 times 5.56 times 10 to the negative 10th, and then you get 3.7 times 10 to the negative 10th. So that's your hydronium ion concentration. It really should be molar. I should have an M after that. So now we're going to go ahead and take the negative log of that number, and you get 9.43. So you can see that up in the initial problem, you have more of the base, the ammonia, 0.15, than the conjugate acid, the NH4 plus, 0.1. So it's going to be a more basic solution. And that's what you see. You get a pH above 7, 9.43. Okay, same problem using Henderson Hasselbach. Since we have both concentrations of weak base and weak acid, conjugates of each other, you can use Henderson Hasselbach. Same calculation. Compute pKa. That's the only thing we don't know that we need for Henderson Hasselbach. So it's negative log of the Ka value that's up in the problem, 5.56 times 10 to the negative 10. You get 9.25. Now you can plug that into Henderson Hasselbach. There's the equation. So it's 9.25 plus the log of the base concentration on the top, that's the ammonia, 0.15, the acid concentration on the bottom, the ammonium. Just do the math on that, and you get 9.25 plus 0.17. So there you go. Okay, it's 9.42. Remember, if the concentrations of the base and the acid had been equal, let's say they had both been 0.15, then the log of 0.15 over 0.15 would have been 0, and your pH would have been the same as your pKa. But they're not equal. You have more of the base than of the acid, and therefore the pH is not going to be the same as the pKa. It's going to go up. It's going to go from 9.25 up to 9.42. All right, so that's how you do these. Real simple. You want to use Henderson Hasselbach if you can, and you can whenever you have concentrations of both acid and base conjugates. So Henderson Hasselbach does not require use of a rice table and can only be used for a conjugate acid-base pair of buffers. Just re-emphasizing that point. Okay, new problem. This one looks a little more challenging, but you just have to step back and think about what you can do to make it simpler. So you're going to use Henderson Hasselbach. So I tell you that up at the top. So how do you know that? Well, again, you have the same weak base, ammonia, and the salt of its conjugate acid, that's ammonium chloride, which is going to break apart and produce just the ammonium, NH4 plus. Okay, so this is a conjugate weak acid base pair. So the first question is, first identify the acid and the base in this problem. Do they constitute a buffer? Yes, they do. We saw that in the last problem. The ammonia is the base, conjugate base, and ammonium, NH4 plus, is the conjugate weak acid. They are conjugates of each other, so you can use this for a buffer. Okay, so what we have to do is, for Henderson Hasselbach, again, just ask yourself, what do you need? You need a pKa. Well, we're not given a pKa. In fact, we're not even given a Ka. We're given a Kb. So we need to get from Kb to pKa. And you can use your acid-base roadmap. You should have that in front of you. And you can look at that and figure out a way to get from Kb to pKa. So we need that for Henderson Hasselbach. Next, we need the concentration of the conjugate base. Well, we were given that. That's the easy one. 0.75 molar, that's a concentration, moles per liter, of the ammonia, NH3. So you have that. You need that, you have that. It's the concentration, molar concentration of the base. Now the acid they made harder. They said you have 20 grams of NH4Cl, and you want to produce 500 milliliters of solution. So remember, we need molar concentration. That's moles per liter. So we have a volume in liters there, 500 milliliters. So that's good. We can use that for our molar concentration. But we aren't given moles, we're given grams. But you've been doing this since the beginning of class, converting from grams to moles. Okay, it's a molar mass conversion. So we're going to go ahead and do that, convert from grams to moles. Then we can take that number and put it over the 500 to figure out our molarity of our acid. We will then have a molarity, molar of acid. We already were given, we just said, a molarity of base, and we can use the Kb to figure out the pKa. So there's a few steps to this, but again, you just have to look at the Henderson-Hasselbach equation, see what is it saying that it needs, and then figure out how to get that. So here we go. So ammonia, NH3 is a base. The conjugate weak base of NH3 is NH4+. NH4Cl, it's ammonium chloride, is an acidic salt because the chloride ion Cl neutralizes the NH4+. In addition, solubility rules tell us that NH4+ and Cl- will completely break apart in water. So NH3 and NH4+ will form a buffer at the pKa of NH4+. That's assuming you use equal amounts. We may or may not be doing that here, but that's conditional that you use equal amounts. Then the pH will be a buffer at the pKa of NH4+. So Henderson-Hasselbach requires a pKa of an acid, never a pKa of a conjugate base. So that Kb up there, we can't just turn that into a pKb and use Henderson-Hasselbach. You have to get it to a pKa for Henderson-Hasselbach. Okay, so we continue. So there's Henderson-Hasselbach. So to use Henderson-Hasselbach, we need three things. The concentration of the weak base, NH3. We said we already have that, 0.75. Okay, and we proceed. So we need the pKa value, but are given Kb. So use the formula Ka times Kb equals Kw. That's on your acid-base roadmap. You're going to solve it for Ka. So Ka equals Kw, which is the autoionization constant of water. That's 10 to the minus 14th over the Kb we were given up above in the problem. You do the math, you get 5.68 times 10 to the negative 10th. That's the Ka value. So you take the pKa, is going to be the negative log of that number, and that's going to be 9.246. So we found the second thing that we need to use Henderson-Hasselbach. That's the pKa. Now we need to find the molar concentration of the conjugate weak acid, the NH4. So we're going to go ahead and first calculate the number of moles of NH4Cl. So the molar mass of NH4Cl, there's 1 nitrogen at 14.01. You get that off the periodic table. There's 4 hydrogen at 1.01. And there's 1 chlorine at 35.45. Now, even though the chlorine is a spectator ion, it's going to break off and float off to the side. You still have to use it to compute the molar mass of the ammonium chloride molecule. So you add all that up, you get the molar mass of ammonium chloride is 53.5 grams per mole. So there we go. We're going to put the 53.5 grams ammonium chloride on the bottom and the 1 mole ammonium chloride on the top. Again, you just the equivalents that you create that. The grams of ammonium chloride cancel out and you end up with moles of ammonium chloride, which is 0.374 moles of ammonium chloride. Now remember, concentration isn't moles, it's molar, it's moles per liter. But we have a volume in milliliters up there of 500 milliliters. You ought to get really good just naturally of converting from milliliters to liters. You just slide the decimal 3 places to the left, and in the case of this, you would get 500 milliliters equals 0.5 liters. You should be able to do that in your head. It's not something you want to spend a lot of time doing a conversion on an AP exam. Okay, so we move on. So since the Cl minus, the chloride, and the ammonium completely dissociate, if we have 0.374 moles of ammonium chloride, that means we're also going to have 0.374 moles of the ammonium ion. We don't care about the chloride ion. We need the concentration of NH4+ for Henderson-Hasselbach. So we are given that there are 500 milliliters of solution. And again, learn to do this concentration quickly. Slide the decimal 3 places to the left. That's 0.5 liters of solution. Why? Because most measurements in chemistry in a lab are done in milliliters, but molarity is in liters. So you're going to have to just quickly make that conversion many times when you do this type of chemistry. So there we go for the concentration. It's moles per liter, so 0.374 moles of ammonium over 0.5 liters of solution gives us 0.748 moles per liter. Okay, so 0.374 moles of ammonium over 0.5 liters of solution, that's moles per liter, that's molarity, so you have 0.748 molar. So that's the concentration of the weak acid. So now we have everything we need. Concentration of weak base, concentration of weak acid, and the pKa. So now we're ready to plug it in. So we have everything we need for Henderson Hasselbach. So it's 9.246 plus log of 0.75. That's the base on top, the ammonia. And the 0.748, that's the acid, ammonium, on the bottom. And you do the math, and all the pH did was go up very, very slightly. So you end up with 9.247. All right, problem 8. Calculate the pH of a buffer of 1 molar CH3COONA and 1 molar CH3COOH. You got to have a Ka value of the acetic acid, the CH3COOH, right there. So we're going to do it using a rice table. Now, what do you recognize about this? It's buffered at a place where the molarity of the base, the conjugate weak base, and the conjugate weak acid are equal. That's generally what you want. Why? Because you want to protect the pH of the solution from both directions. If you get strong acid coming in, then the conjugate weak base will neutralize that. If you got a strong base coming in, then the conjugate weak acid will neutralize that. So you notice you have equal concentrations there. How do you know whether you want 1 molar, 2 molars, or 3 molars, or 10 molar? It depends on how much of the acid, the invader acid, strong acid, or the invader strong base you expect to come in. That's what determine how much of the buffer that you use. Okay, so we're going to do it using a rice table. You see we have a weak acid dissociation there, acetic acid and water. The H at the end of acetic acid jumps over to the water to become a hydronium ion, H3O+, and it leaves behind the conjugate weak base at the acetate ion, CH3COO-. So let's start filling it in. So we start off with 1 molar of both the acetic acid and the acetate ion, nothing on the hydronium ion. And then the usual change line here, negative X, plus X, plus X. 1 minus X for the reactant. 1 plus X for the acetate ion. And 0 plus X is X for the hydronium ion. There's the law of mass action written for the formula. Now we're going to plug in the algebraic expressions. There they are. I think this is all becoming routine for you by now, I hope. Those X's, the plus X and the minus X, are going to be eliminated because they're very small compared to 1. So there you go, simplifying assumption. So what you simply end up with is X on the top and 1 on the bottom. And that's going to equal the Ka, which is 1.8 times 10 to the negative 5th. So if you look over there, the hydronium ion concentration at equilibrium is X. So you simply can substitute that X equals the hydronium ion concentration, which equals 1.8 times 10 to the negative 5th. So you take the negative log of that, and you get the pH, and the pH equals 4.75. We've seen that number before. We've used acetic acid quite a few times, and we've seen that the pH is 4.75, which means if you want to use a buffer of equal concentrations of the acid and the base, then you want to pick an acid that has a pKa equal to the pH that you want to buffer at. So if you want to buffer at 4.75, you pick acetic acid and you use equal concentrations, and that will give you a pH of 4.75. Okay, so now we're doing the same thing with Henderson Hasselbach. So we have the concentrations we need for the weak acid, weak base. We just need to figure out calculate the pKa from the Ka value given there. So the pKa is the negative log of 1.8 times 10 to the negative fifth. That equals 4.75. There's the formula. Plug in 4.75. The log of the base over the acid is 1. So the log of 1 over 1 equals log of 1. That equals 0. Therefore, the pH is 4.75. So if you want to buffer your pH at 4.75, you find an acid that has a pKa of 4.75. That would be acetic acid. And you use equal concentrations. It doesn't have to be 1 molar over 1 molar. It could have been 2 over 2, 10 over 10, 15 over 15. As long as the concentrations are equal, then the log of that will become log of 1, and log of 1 is 0. So you'll end up with a pH equal to the pKa of the acid. And there it is. And that takes care of this problem set. We'll practice some more of these before the end of the semester. If you can master these problems and really gain an understanding of how acids, bases, and buffers work, you're on your way to passing the AP and doing very well. All right, we'll see you on the next lesson.